Alrighty, how are you all doing this morning?
Doing fine.
So I believe we are at the point where we're covering like resistor combination techniques and all that kind of good stuff. So this is really pretty much the last bit of review, as it were, for what you learned in your Engineering 120 series. So is there any questions or anything about how to combine resistors in parallel and series and simplify resistive networks and all that kind of good stuff?
I did have one question about one of the problems in section 2, homework section 2. Give me a second to pull it up. I forget which one.
Let's see. So
it was number 2, the one that's kind of twisted up, the circuit that's twisted, and I got it untangled, but then I don't really know how to start from there.
Okay. So let me open up a new Dropbox. All right. So we have a circuit. And originally it looked something like this. And you're asked to find Ix, which is defined as this current, the voltage, Vx, which I've already defined, and then the power supplied by V1. So you're absolutely correct. The first thing that you should do, untwist this circuit. So I'm going to draw the untwisted version down here. So we're going to have our 25 ohm resistor is going to stay in its same spot. Our 100 ohm resistor is going to be up here. And our V1 voltage source will be down here. And we can see that the 100 ohm resistor is connected directly to a 200 ohm resistor. So that's going to be this guy. And as we follow the 200 ohm resistor around, we see that the other leg of the 200 ohm resistor is connected to the negative polarity terminal of voltage source V2. And then we have, from the positive polarity voltage side of V2, we have a 50 ohm resistor where the positive polarity terminal of the voltage Vx is on the same node as the positive polarity voltage V2. So this is going to be plus Vx and minus. And then the other leg of the 50 ohm resistor is connected to the positive polarity terminal of V1. So this is the untwisted version of the circuit. And now we need to make sure that we're labeling the current Ix correctly. So Ix flows from the 200 ohm resistor to the 100 ohm resistor. So this is our current Ix. So this is a single loop circuit because all of the elements are directly connected together in series. So what I'm going to do is I'm going to write the Kirchhoff's voltage law equation where I'm going to follow that current Ix around this single loop in the direction that's indicated, so in a counterclockwise direction. So I'm just going to start where Ix is currently labeled on the drawing, right? And I'm making the assumption that the voltage drops over these resistors. So let's call this guy V100. The current's flowing into the positive polarity terminal for this guy, V25. The current's flowing into the positive polarity terminal. And over here, this unlabeled voltage, V200, the current is also flowing into the positive polarity terminal. So when I write my KVL equation, I'm going to see V100 plus V25 minus V1 minus Vx plus V2 plus V200 is equal to 0. And a lot of these values are unknown. So this is unknown, this is unknown. V1 was given to us, Vx is unknown, V2 is given to us, and V200 is unknown. So what I'm going to do now is I'm going to apply Ohm's law and rewrite the expression for all of those unknown voltages in terms of the current Ix. So V100 would be the current flowing into the positive polarity terminal multiplied by the resistance of 100 ohms. So it would be 100 ohms times Ix. And we do the same thing for V25, so that would be 25 ohms times Ix. And I'm going to move my known voltages V1 and V2 to the other side. So when I, other side of the equal sign. So if I have negative V1 here, this will be positive V1. And when I move V2 over, it'll be minus V2, like so. Vx, the current Ix is flowing into the negative polarity terminal. So that means I'm going to have minus 50 ohms times Ix. And then the current Ix is flowing into the positive polarity terminal for the 200 ohm resistor. So that's plus 200 ohms Ix. And now I have one equation.
I have a question.
Yes.
Since it was already negative and it was flowing into the negative terminal, why don't those negatives cancel each other out for the Vx?
What's already negative? The current is flowing into the negative polarity terminal, but Ix isn't negative, it's just flowing to the left.
Okay.
We don't know what the magnitude is. So I'm under the assumption that that current Ix is positive and it's flowing counterclockwise around the loop.
Okay,
and that's why I've made all of the voltage drops for the other resistors, the current to flow into the positive polarity terminal. So I'm assuming, because I don't know anything different, that the current Ix has a positive magnitude. And so if it flows into the positive polarity terminal of all of the other resistors that don't have a defined voltage polarity, that those resistors will be absorbing power. So really the assumption I'm making here is that Vx is probably going to be negative based on the direction of the current.
I got it, thank you.
So I can group like terms here. So 100 plus 25 minus 50 plus 200. So let's see, that's 325 minus 50 is 275 ohms times Ix is equal to whatever V1 minus V2 is. And at this point, it should be pretty easy to solve for Ix. Once we know Ix, then Vx is simply negative 50 ohms times Ix. Again, because the current is flowing into the negative polarity terminal, so we need to have that negative sign. and then the power absorbed by the 3-volt source. So the power absorbed by V1 is going to be negative Ix times V1, and it's negative because the current is flowing into the negative polarity terminal, and we're asked to find the absorbed power.
Got it. Thank you for the help.
No problem. Any other questions regarding any of the homework sets or anything thus far?
Yeah, I was struggling with number 4 on the same homework set.
Alrighty.
I think the problem that I'm having is that I can't get IZ in terms of VX.
Okay. So let's scroll down here. That might have been too aggressive. So we have this current I1. This current is Ix, and this is a 20 ohm resistor. 12 ohm resistor with Iy. Current source I2. Dependent current source. This is IZ, and this is 0.25. So this is a single node pair circuit where everything is connected in parallel, and we're also told that there's going to be some voltage drop, Vx, positive polarity on bottom, negative polarity on top. So what I'm going to do is I'm going to work this problem under the assumption that all of the currents that are exiting the top node are positive, and all of the currents that are entering the top node are negative. So my Kcl equation at the top node would be I1 plus Ix plus Iy minus I2 plus Iz is equal to 0. And I have several unknowns again.
Why didn't you include the dependent, the VCCS at the end?
So I could. So I'll write down an alternative expression, and these will be exactly identical. Okay. So I1 just as before, plus Ix just as before, plus Iy, minus I2, minus 0.25 Vx.
So how do you know that those two currents effectively are the same thing?
They're the same but opposite because they're flowing through the same branch. So those currents are flowing through the same element, but they're in opposite directions.
Oh,
Right?
okay.
So your equation, one of the equations that we're going to get that we're going to have to substitute in is going to be Iz is equal to negative 0.25 Vx.
I see. So yeah, that was my problem. I was including both of them in my Kcl equation.
Yeah, so you can't include both because they're representing one current.
Okay.
Just one's flowing up and one's flowing down, but they're in the same quantity.
Will that always be the case in a parallel circuit like this? That two currents flowing in opposite directions through one element are going to be equal and opposite?
So it doesn't matter if it's in any circuit, if we have a current defined effectively twice over one element.
Mm-hmm.
Doesn't matter if it's a parallel circuit, series circuit, or some combination thereof. Those currents will have effectively the same magnitude. Well, I don't want to say this, the same absolute value, right? So you know, one must be positive, so the other has to be negative, and it's because it's in the opposite direction.
Okay. Can you? I don't know. This may not be correct, but this is how I was starting to try to rationalize it was seeing it as like kind of the same way as KVL, where you could say like a closed loop, but maybe like one element, the sum of that is 0. If that made any sense.
So for KVL, you would be having voltage drops that you'd be dealing with, right?
Yeah.
So, I mean, if you do, like if we did a KVL loop in this circuit, any KVL loop really, so this one or this one or this one or this one or whatever, we're going to
Yeah.
find that you're going to have plus Vx minus Vx is equal to 0, which means Vx is equal to Vx.
Mm-hmm.
Right? So that's a way to easily show that when everything is in parallel, the voltage drop is shared among all of the elements. But
Okay.
I don't know if that's going to help us particularly find any of these currents.
Okay.
So we can run with either of these two equations, and then we're going to have to throw this guy in as a substitution, and we're also going to have to use Ohm's law to write an expression for Ix and Iy in terms of Vx. And so those equations, let's see, Ix is going to be negative Vx divided by 20 ohms, where the negative sign comes from the fact that the current is flowing into the negative polarity terminal. And similarly, Iy is equal to negative Vx divided by 12 ohms. If we substitute all three of these relationships, the one for Iz in terms of Vx, the one for Ix in terms of Vx, and the one for Iy in terms of Vx, into either of our original KCl expressions that I've written, we'll have, excuse me, one equation, one unknown. So we could solve for Vx and then use Vx to solve for Ix, Iy, and Iz using these relationships that I've written at the bottom. So in the last example, where we had a single loop circuit, effectively once we knew what the current that was shared among all the elements was, everything else was fairly trivial. And in this example, with a single node pair circuit, once we figured out what the voltage drop was that was shared over all of the elements, all the other calculations were pretty easy too. So anytime you have a single node pair circuit, your best bet is to start trying to work the circuit using Kirchhoff's current law. And anytime you have a single loop circuit, your best bet is to start working the problem using Kirchhoff's voltage law.
Yeah, it sounds good. Thank you.
No problem. Any other questions or anything regarding the homework? Excuse me. All right, nobody's saying much of anything, so let's pop over to the in-class assignment. I think it's just one problem worked a couple of different ways. So we want to find the equivalent resistance between the following terminal pairs, terminals A and B, A and C, and D and E. So between A and B, so this is something that a lot of students typically struggle with at the beginning, and then hopefully they catch on pretty quickly. But people unexperienced in circuits might say, all right, so the resistance between terminals A and B is simply this 1 ohm resistor, and I'm finished with the problem. And that's not true. And the reason it's not true is because you have all of these other resistors connected, and they're effectively going to form a resistive network that is in parallel with that 1 ohm resistor. So what I mean by that is, let's look at this guy over here, right? How are the 18 and 17 ohm resistors connected?
In series?
So let's look. They share this node point in common. And they share this node point in common. So if they share the top node and they share the bottom node, are they in series or are they in parallel?
No, parallel.
Right, okay. And what about the 8 ohm resistor and the 3 ohm resistor? Oh, I can barely see that yellow. Let me use a different color.
Same thing, parallel.
Right. So what we could redraw this as would be our 6 ohm resistor up top, and then 18 in parallel with 17. 8.743. Eight in parallel with 3. .182. Finally in series with that 5 ohm resistor. So this big ugly network really just looks like 6 plus 5 plus 8.742 plus 2.182, 21.925 ohms. And now that we know how this big ugly thing on the right behaves, the rest of the problems should actually be fairly straightforward. So let's switch to black. All right, so we have terminal A, and that's a 1 ohm resistor. Terminal B, 19 ohm resistor. $13. And then that 21.925 ohms guy. Right, so this is the first simplification that we can make. It's technically a couple of simplifications in, but does everybody see where this 21.925 came from and how to do that?
Yes, sir.
Okay, so if we're trying to answer part A, we're trying to find the resistance seen looking into this pair of terminals, A and B. My first question is then, are either of those 13 ohm resistors going to contribute anything to the equivalent resistance?
No,
Why not?
because you can make a loop ignoring it.
So, I mean, you could make a loop ignoring anything if you chose to do that. So the real reason is because one terminal of each of those resistors isn't connected to anything. So, like if you hooked up a voltage source to, or even a current source to terminals A and B, you would never actually see any current flow through that loop. So those resistors are never going to pass any current, so they're not going to affect anything because of that open circuit there in the middle. Now, when we are specifically connecting or looking at the resistance between terminals D and E, if we put in, say, a test voltage or a test current source, that would close that loop, and so they'll start contributing. So for part A, effectively what we have is our 1 ohm resistor. And I'm not going to draw terminal C because it's not going to play any role here. Our 19 ohm resistor. And then our 21.925 ohm resistor over here, where I have neglected to draw the 13 ohm resistors because, again, they don't contribute anything. So it should be a little bit easier to see that the resistance between terminals A and B is going to be our 1 ohm resistor in parallel with the series combination of our 19 ohm resistor and our 21.925 ohm resistor. Just to make hopefully it pretty obvious. So this is one node. This is a second node. This is a third node. And so we can see that the 19 ohm resistor and the 21.925 ohm resistor are in series because they share one common node point with no branching paths. That's how we know it's in series. Once we combined those two, we make those into a single equivalent resistance, then we would only have nodes A and B, and we would see that the 1 ohm resistor is in parallel with the series combination of 19 and 21.925. So if we do the math here, this is going to be 1 ohm multiplied by 19 ohms plus 21.925 ohms divided by 1 ohm plus 19 ohms plus 21.925 ohms, where I've used the shortcut for combining two resistances in parallel. And I'm treating that series combination of 19 and 21.925 as a single resistance. So any questions thus far? All right, nobody's saying anything, so that's goodish news. So if I do the math on this, I'm going to have 19 plus 21.925 divided by 1 plus 19 plus 21.925 is 976.148 milliohms. Let's check. Yep, so 0.976 ohms is 976 milliohms. So that seems legit. Let's see. I need to give myself some more engineering paper. For part B, I'm looking between terminal A. So I have my 1 ohm resistor. Here's where terminal B was. Here's terminal C, my 19 ohm resistor. Again, the two 13 ohm resistors aren't going to contribute anything. And then here's my 21.925 ohm resistor. So who among you can tell me what this equivalent resistance is going to look like?
It should look the same as AB, right?
So I would argue that it's going to be a bit different.
They're all in series. If you do 21.925 and then no,
So
because that branches off of C.
let's see. So this is one node.
Uh-huh.
This
Oh,
is
so
one node.
it's going to be a 20 ohm in parallel with the 21.925.
There we go.
Okay.
Yeah. So we can see that the 19 and 1 are in series because they have that single point of interconnection with no branching paths. So we could combine the 19 and 1, and then that equivalent resistance would be in parallel with the 21.925. That's right. So we'll have 1 ohm plus 19 ohms in parallel with 21.925 ohms. So that will be 1 ohm plus 19 ohms multiplied by 21.925 ohms divided by 1 ohm plus 19 ohms plus 21.925. Parentheses around here, although in the denominator it's really not going to matter there. I get 10.459 ohms. So it's the exact same network, but because we're looking in a different set of terminals, the resistance looks very, very different, right? It's roughly 11 times larger, and all we did was slightly change the way we're looking into the network. So for the last bit, we're no longer looking at terminals A, B, or C. We're looking for the equivalent resistance as seen by D and E. So we have our 1 ohm resistor, our 19 ohm resistor, 13 ohm resistor, here's D, here's E, 13 ohm resistor, and then here is our 21.925 ohm. So any ideas on how we could approach this guy, where we're looking into terminals D and E like so?
We can start off by putting the 1 ohm and the 19 ohm in series.
Okay, so the 1 ohm and the 19 ohm in series are going to look like a single 20 ohm resistor. That's absolutely correct. So by making that simplification, what can we see now?
That everything is in parallel.
So for everything to be in parallel, they would have to share both sets of terminals. So this is one node. This is a second node. Here's a third. And here's a fourth. So we can see that the 20 ohm resistor and the 21.925 ohm resistors are in parallel because they share that, I don't know, ugly green node with the vibrant green node. I'm bad with colors, so I don't know how else to describe them. They share the top node and the bottom node, right? But the 13 ohm resistors are not in parallel because the orange node isn't shared with anything and that purple node isn't shared with anything.
Right. Okay, yeah.
So what we could see here, to simplify our math a little bit, so our previous example, looking at the resistance between A and C, was just the 20 in parallel with the 21.925, right? So this is just 13 ohms in series with that resistance in series with another 13 ohms. So let me really kind of spell that out by redrawing things. So I'm going to put element D up here. Here's my 13 ohm resistor. Here's my 20 ohm resistor. Here's my 21.925 ohm resistor. And then here's my other 13 ohm resistor. Right? So this is the exact same circuit, but redrawn just to make things a little bit clearer. And all I really did was flip these 13 ohm resistors up. The top one I flipped up and the bottom one I flipped down so that it's got a little easier to analyze shape. And now it should be pretty easy to see that it's 13 in series with a parallel combination of 20 and 21.925, which is what we had for RAC. in series with another 13 ohm resistor. So RDE would then be 13 in series with what we had for RAC in series with another 13 ohm resistor is going to be 26 plus 10 is 36.459 ohms, where I'm just using the results from the previous part of the problem in my analysis. That makes sense?
Yes.
All right, so I want to look at maybe a couple of the homework problems from homework set 3 real quick. Not that one. Yeah. So homework set 3, problem number 2. This is a problem that gives students a bit of difficulty, even though it's actually pretty similar to the resistor combination problem that we just did, but I'll still take a look at it. So you have a 100 ohm resistor here, a resistor labeled R2 here, 50 ohm resistor, some resistor R1, 75 ohm resistor, 200 ohm resistor. I'm probably going to regret not drawing this larger in just a second. We'll see. 25 ohm resistor. And we also have a resistor R4 that goes here, and a resistor R3 that goes on that diagonal. And we're given lots of terminals. So this is C, B, A, and D. And you're asked to work this problem multiple times. So you want to find the resistance between terminals A and B, the resistance between terminals A and D, and the resistance between terminals C and D. So let's just work A and D. So our goal is to find R, A, D, and we'll use my numbers. So R1 is 30 ohms, R2 is 180 ohms, R3 is 120 ohms, and R4 is 58 ohms. So I'm going to identify my nodes. So that's going to be node C. Node B. Node A. Node D. Let's call this guy E. And let's call this guy on the right in orange F. So based on how I've labeled all my nodes, what resistor combinations could I make right off the bat?
Node E and node F, you could just convert those into series.
Yeah, so the 100 ohm resistor and the 25 ohm resistor must be in series because node E is, again, a single point of interconnection with no branching paths. So I could replace those two resistors with a single 125 ohm resistor. And similarly, the 75 ohm resistor and the 200 ohm resistor share node F, and it has no branching path, so I could combine them into a single resistor as well. So I could redraw this guy. with 125 ohm resistor here. Let's see, R2 was 180, so I'll just write in 180. R1 is 30. 200 plus 75 is 275. Those resistors are part of the equivalent resistances I see on the outside there. Then I have this guy R4, which is 58. And this guy R3, which is 120. And C, B, A, and D. So I'm going to relabel my nodes. C, B, A, and D. And what can I see now? And again, my goal is to find RAD. Anybody have any clue what the next step may be? All right, so let me rephrase my question because I don't necessarily know what the answer is, but I know how to proceed. The 125 ohm resistor and the 58 ohm resistor, how are they electrically connected?
Parallel.
They're in parallel, right? Okay. And the 120 ohm resistor and the 275 ohm resistor, how are they electrically connected?
They're also in parallel.
Okay, so we have two simplifications that we could make. So 125 in parallel with 58. So let's draw this guy like this. 125 times 58 over 125 plus 58 is 39.617. That's our 180. This guy's our 50. Sorry, I was confusing myself in the way I had drawn the circuit. 30 ohm. And then 120 in parallel with 275. .544 ohms. This is C, B, A, and this bottom guy is still D. So we're making simple resistor combinations just using, looking at the nodes and observing whether or not things are in series or in parallel. So we can continue that process. So here's element C, or excuse me, node C, node B, A, and D. So what is a simplification that we could make now?
the series between the 180 and the 39.617, and then
Right.
the 30 and the 83.
So the 30 and the 83 are in series, but we're not going to touch that one because we're trying to find what the resistance is between A and D. And if we combine those two, we're going to effectively lose some information there that's going to be useful to us. Because if we combine those two, we're going to get rid of node A, which is going to make it impossible for us to solve for resistance AB. Does that make sense?
Yeah.
Yeah. So we want to leave node A alone there. But making that series combination is exactly the right move. So 180 plus 39.617 is going to look like 219.617. Short circuit there. Here's our 50. 30. 83.544. Here's D. So we've gotten rid of node C entirely. So we have B, A, and D, like so. So we should be pretty close to a point to where we can see what's going on and not have to make any more resistor combinations, but I'm still going to go ahead and draw my nodes just so I can make sure of what I'm doing.
Excuse me, Dr. Hartman.
Yes, sir.
This is a little unrelated, but do you post these videos somewhere else?
They are on YouTube, and as soon as I upload them to YouTube, I also upload them to Moodle. So we'll jump back to this example problem in just a second, but let me stop sharing that and start sharing this. So this is our course's Moodle page. So for example, the class meeting that we had on 6/9/2020, so that was last Tuesday, I believe. So click on that link. I should have moved it up top, but down here below where the in-class assignment was to be submitted, this link URL, ENGR 221 class meeting number 3, that is the recording of the Zoom meeting. And then if we go to class meeting number 2. Oh, I put that one where it was supposed to be. So, so this recording, once I finish editing it and upload it, will be in the class meeting number 4 folder, and it'll be posted right after the pre-recorded lecture material and right before the in-class assignment. It does take me some time, so I have to let Zoom finish doing what it does to the video and then send me a link to where I can download it, and then I edit it down just to chop off the couple of minutes before class that nobody's really saying anything and all that kind of stuff, and then I upload that to YouTube and then put a link here on Moodle. So I would anticipate that this recording will be up probably sometime around 3 or 4 p.m. today.
Okay, thank you so much.
No problem. So let's jump back to that example problem. There we go. And I've also got node A that I should label right here. All right. So our ultimate goal here, I'm running out of paper or virtual paper or whatever you want to call it at this point. So we're trying to, RAD. Although this would be a pretty decent point for the analysis for RAB as well, which is part A of this problem. But anyway, so effectively what we're trying to do is we're trying to get all the rest of this network to look like it's in parallel with this resistor that's directly placed between nodes A and D. So how could we simplify things to make that happen?
The 219 and then the 50 are in parallel, and then once we do that, the 30 and then the result of that are in series.
That's absolutely correct. Perfect. So what that gentleman suggested was we would combine the 219 and 50 in parallel, and that would be in series with the 30, and then that total equivalent resistance would be in parallel with the 83.544. So mathematically, let's walk through that. I'm going to have 83.544 ohms in parallel with 30 ohms in series with 50 ohms in parallel with 219.617 ohms. This is going to be a bit of an ugly expression, but we will make it work. So I'm going to have 83.544 multiplied by 30 plus 50 times 219.617 divided by 50 plus 219.617, close that guy off, divided by 83.544 plus, and I'm just going to draw an arrow here because I'm running out of stuff, this term in the large parentheses. And that will be my equivalent resistance, where I've skipped a couple of steps, although the gentleman that responded answered exactly how to do it. Yeah, so we've got our resultant equivalent resistance. So the reason why I looked over this one is because this problem is rife with people, even though they've had practice doing resistor combination techniques. I guess because it looks ugly and maybe they don't want to try, they would typically say that the resistance between A and D is just that R3 value and try to not actually work through things. And it's important to recognize that even if there is a resistor directly connecting those terminals, you still have to account for everything else. So the goal for this particular problem was how to make the rest of the network be in parallel with that resistor R3. Similarly to how part A of the problem, finding the equivalent resistance with respect to terminals A and B, is how to put everything in parallel with resistor R1, etc. So any questions on this resistor combination problem? Nobody's saying much anything. All right, so let me look at web work one last time, because I think there's another problem that typically jumps out and confuses a few students. That one's annoying, but it's not too bad. That's not the one I'm thinking of. I wonder what homework set it's on.
Hey, Dr. Hartman, what's the answer for it? Just so I can check.
Oh, all right. So give me just a moment to scroll back down here and throw it in my calculator. That's a great question. Let's find out the answer here. So let's see. I'm going to use my calculator and store some things as variables to make my life a little bit easier. All right, so I'm going to have x multiplied by 30 plus 50 times y 50 plus. So so I got 38.302 ohms, assuming I didn't fat finger a wrong number on my calculator.
That's what I got as well. So
Okay, cool deal. All right, I'm trying to, so there's a problem somewhere with like crisscrossed resistors that likes to trip people up. I'm trying to find it. Here we go. All right, so this is a document, append, add, let's see. Homework 4, problem 2C. Where we have a 20 ohm resistor. This resistor is just labeled R, and R is 25 ohms. Okay. Oh, let me redraw that middle line there because it wasn't clear that it was jumping over. That looks a little bit better. So this is a problem. It's in your homework. I get questions about. I have previously used it on a test before, but I wouldn't count on me doing that again. I just wanted to go over it because it tends to confuse people. And so how I'm going to approach this is much like I did the last problem. So we're trying to find, let's call this A and B. We're trying to find the equivalent resistance seen between those terminals. So I'm going to identify my nodes. And so this is going to be one node. This is going to be another node. That's a node. That's a node. And that's a node. And then I also have the nodes A and B, but I'm not going to worry about them too much because they're pretty obvious. They're already labeled. So one thing to think about on how we can redraw this circuit, let me put some labels on it. So that's A and B. This guy is C, which means this guy is also C. This guy is D. This guy is E, which means this guy is also E. F and G. So what we could do, so the first thing that we could do pretty obviously is observe that node D is a single point of connection with no branching paths, which means that 25 ohm resistor and that 10 ohm resistor form a single 35 ohm resistance. Similarly, node F is a single point of interconnection with no branching paths. So between E and C, we will have, on the right-hand side, we will have a 75 ohm resistance. And node G is the interconnection point for a series resistance of 30 and 25 is 55. So I could redraw this guy as, here's 20, 25 and 10, I believe makes 35. $25 and 50 makes 75. 30 and 25 makes 55. That looks awful. And then finally over here, we have our 16 ohm resistor, and then our crystal bits, where this is C, C, E, and E, like so. So let's see, I used this green for C. This green for E. And so this big ugly looking thing, we can now actually observe pretty easily that the 35 ohm resistor, the 55 ohm resistor, and the 75 ohm resistor, how are they connected?
They're in parallel.
Yeah, they're all in parallel because they all share the puke green node and the forest green node. So this ugly looking thing actually simplifies down to this, which is actually pretty trivial to solve. So I don't usually go with weird crisscrossing things like that on tests, but just be aware that in your homeworks and stuff like that, I guess Dr. Hummel thinks that those kind of things are fair game. So what I like to do by identifying my nodes and attributing them different colors, to me, makes it really easy to see whether things are connected in series or in parallels. It's more helpful for parallel connections, actually, because I can see, well, they all share this green and they all share that one, so they have to be in parallel. So as long as you're using different colors for different nodes, it's actually pretty trivial to figure out whether things are in series, parallel, or neither. Yeah, I just wanted to work that example problem where something that looks pretty horrible at the beginning, you can find out that you can redraw it in a very, very simplified fashion. Oops, I'm missing a 16 ohm resistor here. I apologize for that. Just by well labeling and identifying your nodes. All right, so that's an hour of gibberish out of me regarding resistor combinations. So I feel like that's probably enough, unless you guys have any further questions. All right, nobody's saying much of anything. So if you have any questions on the web work and stuff over the weekend, feel free to shoot me an email, and I'll either send you an email back or I'll try to address it at the beginning of class on Monday afternoon. If you don't have any questions, that's great. Just have a great weekend, and see you all Monday.
Thank you.
All right, you guys have a great
Thanks,
rest of your day.
Have a good one.